All right, so now that we're officially recording, thank you. Appreciate your patience on trying to get all of the technology going. Welcome to our first live and online meeting presentation. We are at the Southeast Regional Library with looks like 40 people or so, thereabouts. And I'm not sure how many have logged on, Tom, with the online Zoom. And today the agenda is general welcomes, introductions, current business. We have a member presentation from Tom Polakis, and then our featured speaker is Paul Knauth. Deep Time, the Universe, Table Salt, and the Prospects of Life as We Know It Elsewhere. It's a long title. Not sure how long the presentation is, but it's an intriguing title.
We've got 48 online, Claude.
48 online. Okay, great. That is good. Officers and board. I am Claude Haynes, your president, and VP is open. Thanks, thanking Tom Mosden for still kind of acting VP and helping us with the technology of the Zoom meetings. Our secretary is Gordon Rosner in the back. And our treasurer is also in the back, Alexandra Nachman. First time some of you get to see her because she's fairly new to the club. And our board members, wave or stand, Dave Kosho, John Kester, Bill Peters, Brooke Schofield, Derek Youngson. Derek sends his regrets from Aruba, so I asked him to raise a margarita in our honor. So we can all feel sorry for Derek on his vacation. James Yoder is our property director, and he's also helping out with the cameras. And Alexandra is also our events coordinator. And then Marty Pazanka is the webmaster and newsletter editor, and has been for a long time. So we appreciate that. Tonight, logistics for in-person. Shirts are on the table in the back. They're the logoed shirt. So I'm modeling our shirts. They're various colors. Generally, shirts are $15. The 2XLs are $18. Caps are $10. There is a sticky note on each of them. So just take that with your payment over to Alex. That helps us with a little bit of inventory control. There's a bunch of magazines that are free on a table in the back. And also a member had a video on astrophotography that he was donating as well. Near the front, you saw as you came in badges, they're on the table, and then see Alexandra for any other dues or other things in the back. But if you are doing business, please keep it down a little. We are not doing a break, so we're going to go through the meeting straight through. We decided not to do refreshments. We may change that for next month, but for this month, we're just going to go straight through. We are doing a few outreach events. Don, Alex, and I went to Carefree for Earth Day. We really enjoyed the huge inflatable Smokey the Bear from the Forest Service. We were doing solar viewing. And then I spent last Saturday at the Science Center downtown, passing out flyers for Greco and talking about the lunar eclipse that was coming up the next night. And then for the lunar eclipse, we had a lot of great folks who helped us by donating, bringing telescopes so that people could see, since it wasn't moonrise and the moon was going to be low for the observatory. We had like almost, I would say 300 to 400 people. It was a big night. We did almost 200 at the observatory, but a lot of people just didn't come up. They were just down looking through the other telescopes. It was a really great event, and we do appreciate everybody's help with that. The Grand Canyon Star Party is coming up in June 18th through the 25th. The South Rim coordinator is Jim O'Connor. He is with the Tucson Amateur Astronomy Association. Just visit their site and you can log in there and fill out the form to get your name on the list. There are forms to fill out because you are a volunteer for the National Park Service. You are responsible for your own accommodations. I'm not sure how full it is, but I didn't have any trouble a couple of weeks ago reserving room. If you're interested in the North Rim party, that's sponsored by SAC. And if you know Steve Dotter, you can contact Steve. I think he is full, but I don't know for sure. But the North Rim is fun also. It's a much smaller site though. The South Rim is a really busy place. Summer family events we have coming up on June 27th and July 25th. This is in conjunction with the library. So we'll be meeting here for a short lecture, 30, 45 minutes, and then doing observing afterwards. This is designed for families. So if you have people with kids and they want to do things, this also counts for summer reading time. So it's a fun thing for people to do. And then our member presentation. It's amazing what you can find on the web, Tom. So we're here for maximum embarrassment. I am now going to switch over. I'm going to stop this one.
Okay, so I am working at Lowell Observatory part-time, and here was the employment timeline. So I was hired way back in September of 2019, and then I was supposed to use a camera on the 42-inch, and it blew up about a week or two later. And then that lasted until, unfortunately, March of 2020, and we all know what happened then. So then when I really got hired after all that was about 1 year ago, 13 months ago. And it was to operate the 42-inch telescope for 2 weeks per month. And that was going pretty well through about the monsoon. And then they changed my assignment to something involving amateur telescopes, which I really like, involving Celestron 14s. And that's what I'm going to talk about. This up higher. All right. On to the next slide. All right. So what is seeing better? Okay. What is seeing? You see Jupiter twinkling away, and we're all used to that as amateur astronomers. You look through a telescope and nothing stands still. That's part of the reason why we have Hubble and James Webb Space Telescopes and all those others. And in the middle between Jupiter and that 3D diagram is a star magnified really close up to just see the star. So if the seeing is good and the air is stable, that star all the light will be concentrated into this real narrow point spread function, they call it. And that's what that little diagram is for. And if the seeing's bad, like we always have down here in the valley, it'll be really spread out. And so it just gets measured as what's the width of that disk is a simple way of looking at it. So seeing is not transparency or darkness. It's just how stable the sky is. So seeing is air aloft. It's a jet stream moving overhead. It's fronts going through. It's your local terrain. If you're in a river valley, it's almost always going to be bad as drainage goes down that valley. And then it's what you have the telescope situated inside of. And we've gotten way better at that in the last 20 to 30 years of making enclosures that are not ruinous to the seeing. Domes are generally terrible for causing their own seeing. But what we're going to talk about is just the local terrain. So Lowell is going to install a 1 meter telescope. It looks like maybe like a plane wave or something on Anderson Mesa. They've been given a sum of money, and I'll put a 1 meter up there and put it at the best site that you have on Anderson Mesa. And so there's two sites. There's two candidate sites. Both of these domes have obsolete telescopes. One's a 31-inch. That's 40, 50 years old. Another is the Lonios, which was a survey telescope that discovered asteroids in the 90s. And both of those telescopes have been decommissioned and they're just sitting inside the dome. What we want to know is which of those two sites that are a quarter mile apart, which of those sites has better seeing, or is it the same? And then we'll pursue putting the telescope at the better of those two sites. You don't want to build a new dome up there because that involves the bureaucracy of the Forest Service. You don't just throw stuff up as you want. So they'll use an existing dome. So just all I'm going to talk about in the presentation is how I got the data, the sites, a little bit more about that, and then how we moved it over to the Lowell Discovery Telescope, which is their 4 meter flagship telescope by Happy Jack down the road from Anderson Mesa. So here's a little bit of seeing theory and dim theory. So it is called a differential image motion measurement. And what you do is you take a telescope that's say 14-inch and you cut 2 4-inch holes in a mask. one of those holes will have optical wedge, which displaces the starlight a little bit. And what you get at the focus is two perfectly focused star images, but they're displaced from each other. And the seeing, after you do a little bit of math, is how much are those two stars moving relative to each other. So you get a differential motion. So you set up a garden variety webcam that we use for planetary imaging. You record 1,000 frames. Each one of those frames, if I knew how to do anything with Python, I'd write a Python script, and that's what has been done. You would look at what's the distance between the centroids of the two star images 1,000 times, and the variation in that, if it's large, that means the seeing's bad. And if it's real small, like it is at Anderson Mesa, you barely see any movement at all. And so that's really all it is. And what's nice about it is you can put it on like a Celestron 14 that's reasonably portable and move it around to different sites. It's immune to wind or shakiness of the mount, since that's moving, both of the star images are moving in with each other. So there's our optical wedge that we used on the C14. And the DIM, as I mentioned, is just a mask. We just use a CMOS camera, planetary camera, we call those. It's real simple equipment that you end up using for this. And you usually sit outside with it and operate it. So that's what the two star images look like in the animation. You notice the tracking's not real good, so they're kind of moving over to the west a little bit. But you can see that doesn't matter because you're measuring how much do they vary relative to each other. This is an example of about 1 arcsecond seeing, which is real good. We get 2.5 to 3 most of the time in my backyard in Tempe. They'd be jumping all over the place when that's the case. So that's kind of my schematic of how the whole thing works. And the bottom line, the thing that you're trying to do is create that figure down at the lower right corner, which is versus time. What's the seeing done during the night? And then we're going to have two sites, those two sites that are 1/4 mile apart from each other, and compare that. What do those two plots look like overlaid? A little bit about these sites that I mentioned. Everybody's in the Flagstaff, and we all know where Mars Hill is up on the west edge of Flagstaff. And that's where the giant new visitor center is currently being built. And that's where they do the visitor experience stuff. But the real science gets done at Anderson Mesa down the road. It's only 9 miles. I spent a lot of clear, dark nights at Anderson Mesa. It's 9 miles from Flagstaff. From a city with 80,000 people, and it's 0.3 of a magnitude above natural. So the sky brightness, you can go to the middle of the Pacific Ocean, would only be a few tenths of a magnitude darker than it is in Flagstaff. And that's 100% due to Chris Luganbuehl, who is at every city council meeting that has to do with light pollution. And they have the best lighting ordinance in the world for that reason. Down the road by Happy Jack is the Lowell Discovery Telescope. That's a 4.3 meter telescope, real modern, and that's their flagship scope that is oversubscribed. And that's where I've been working just 3 nights a month in the past few months. They let me fly the drone around. That's the site at Anderson Mesa. You can see the usual forest fire going off on the horizon. That's the San Francisco peaks with Mount Eldon in the foreground, and see the Lonios and 31-inch are the two domes that they're going to have as the candidates for the 1 meter telescope. 72-inch is now owned by Boston University, and the 42-inch is owned by Lowell. That it only has 2 people who ever use it, Dave Schleicher and Brian Skiff, and nobody else cares about it, but keeps going. There's the 2 sites with the Celestron 14 set out. The Lonius on the left, we had an old fork-mounted C14, which is back when I was like 16 years old. I used to see those ads that had the 4 Celestron models, and a C14 cost $7,000. And I was like, oh yes, it will be mine one day. And now that I've used them, they're just junk. I mean, it's amazing how bad they track and point and shake in the wind. And so Mike Collins, who people should know from here pretty well locally, has been working for Lowell for the past 4 or 5 years. He lent out his Astrophysics 1200 mount, which is what you see on the right side. And that's just been golden. That's been great to use that. So fortunately, somebody else got the privilege of running the fork mount. And then I went over to the 31 inch on the right and got to use the good mount. So that was nice. Here's what an output plot looks like of seeing at the two domes. So Lonios dome in green, 31 inch dome in red. One thing I didn't mention was that the result that everybody's cheering for, everybody wants, is we want it to be the Lonios dome because it's can kind of see the edge of it on the left illustration is sheet metal and is much better at not retaining heat than the big brick thing that the 31 inch, which really mucks up the seeing. So you're making this measurement and then you put it in a dome and the dome ruins the seeing. That's not what we want. So we want the Lonios to be the winner, but we're being scientists here and we're going to find out who really is. And so on a typical night, there wasn't a clear winner and there's quite a bit of scatter as you go through that night. So this is a October night. So we would start at 7 at night or so and then go on through morning twilight sometimes, or 3 or 4 in the morning usually. And this is what you always have as your deliverable. If you ever see a paper that's written about seeing conditions, it's going to be a histogram of the seeing. And what you're seeing there, is a median seeing, which is the 4th row down in that table at the Lonios dome that's effectively about the same as it is at the 31 inch. I think people are surprised that it's as good as it is because it certainly is not. When you go inside the 42 inch, it's never as good as one, or it's rarely as good as 1 arc second. It's usually 2 or 2.5. So that's all dome seeing that's causing the problems. The site is actually on these same nights that we were measuring is really good. It's arc second seeing. And this is only a 400-foot rise above Lake Mary Road. So it's real. It's not like you drive 6,000 feet up a peak or anything. It's just barely above the surrounding terrain. And that's all you need to have good seeing in Arizona, is be in northern Arizona and just be a little bit above it. I guess the title's getting blocked. I don't know how to change that. I don't care. What I did on one night, we had only one observer, me, show up because the other observer, astronomer, doesn't like working weekends. So, and when it's perfectly clear. And so I just went anyway. And I said, the thing I'm going to try all night is I'm just going to point there, and just do a sequence of stars that start near the zenith, 80 degrees, 90 degrees, and then go all the way down to 6 air masses, which is about 10 degrees. And then see what we get for the seeing as you go from the zenith down to near the horizon. How much does it deteriorate? And then I'll do that every hour for I guess I did it for 7 hours. I did 7 different discrete measurements. And what we got then as a result looks something like this, where now you're looking at air masses, which is the x-axis, but I've labeled altitude. So the zenith is all the way on the left. And what you can see is we have 1/2 to 1 arc second seeing. And the main takeaway from this, my data points are all those blue points. Forget about the curves right now. The main thing that you see is that as you only go to 30 degrees altitude, right there, you've made the seeing twice as bad. So for amateur astronomers, and I see this all the time, the Ring Nebula is 15 degrees above the horizon. The M13 is 20 degrees above the horizon. Just wait 2 or 3 months and it'll be a lot higher, or wait 2 or 3 hours in the night, because you're really getting a compromised view by looking at things that are low to the horizon. So the only time you should be looking low to the horizon, unless you don't have any opportunities other than that to get out, is when it's like a transient object, like a comet in the morning sky or evening sky, or it's the southern horizon where you can't do anything about it. So it really showed a lot of deterioration just going from the zenith down to 30 degrees. With the model, there's actually a turbulence model that Stephen Levine gave me. That's the red curve. And it's sort of lined up with my hokey little curve fit that I did in Excel. So anyway, then what we did was, that's a conclusions thing. And I've already said all these conclusions, so I'm going to move on. Then we went to the Lowell Discovery Telescope. And so since, what was that? I guess last December was my first trip up there, when there was, of course, it was fresh after a snowstorm when I arrived. We moved that shed that you see in both of those drone pictures that I took And that shed, the whole thing rolls off, and then there's a C-14 under it. And we did similar measurements. And in this case, the purpose, we already have the site. But what we want to do is see if we can figure out how much the seeing is deteriorating from, or how much it's different from the ambient air to inside the dome. Like how much is the dome doing to that? And we know that's not much because it's a modern, well-designed, well-ventilated dome. But we want to see what it is. And there are a couple other purposes that involve adaptive optics that may happen on this telescope in the future. So what we did was, in this case, we ran the same kind of tests, but then somebody who knows more than any of us, Tom Bida up there, told us we should change the shutter speed. Tried for our camera 2 milliseconds, 10 milliseconds, 20, and that's going to give you a different result. And it's going to tell us something about the frequency of the seeing of the turbulence. And so we did a little bit of that as well. Here's our histogram for the Lowell Discovery Telescope. And I guess talking is getting blocked. Yeah, you can see the median. And this is an amazing coincidence. There was a 15-month survey in 2002 as a site survey before they built the Lowell Discovery Telescope. And the median seeing was 0.84 arc seconds. And then here's 0.84 and it happens again. So I didn't fudge anything. It's just how it came out. And so that's what we ended up with. And that's a great observing site. That's like going to Chile. That's a Paranal or La Silla, going to a great site, world observing site. And there's this myth that people, especially in Florida, think you have to go to Florida to get good seeing. Well, here we are, in this case, less than 200 feet above the surrounding terrain with a paved road, you know, hour away from Flagstaff, and it seems this good all the time. The median is point. And when I was there one night, they can always measure it during the night. And the observer, the remote observer, asked what the seeing was, and they just couldn't believe it. It was 0.55 arc seconds. So there's almost no image motion. It's like being in space. So I just got some conclusions right there. If they are, hopefully, they will pursue adaptive optics on, right now they have active optics with the actuators on the back of the mirror of the Lowell Discovery Telescope, but maybe they'll pursue adaptive optics. And in that case, this business with the different shutter speeds will really help out on that. So I think that's mainly what I got. Can I go 5 or 10 more minutes? Okay, yeah. And then what people more would want to see than this heavily technical presentation, one of the motivations for me wanting to still go up there is that they let me take my camera anywhere, like to the dome floor and everything, and drone flights and all sorts of cool stuff. So I just have some miscellaneous photos of the Lowell Discovery Telescope. There's Jennifer and me doing a selfie in front of the scope. It's a beautiful dome. You barely hear any noise when it rotates, and same with the telescope when you're inside, and everything. There's anything this complicated has constant technical issues, but when it's working, which is most of the time, the pointing and the tracking and the optics are just terrific. So it's competitive with any world 4-meter telescope. And especially this past year, nobody should be complaining about clouds because we've had really nice, clear, dry weather. And of course, we're going to run out of water, but that's a different issue. So just a couple shots. There's the Little Dipper above the Discovery Telescope. I believe it was 9 degrees when I took this photo. So I don't do cold weather in general. So it's really nice to be out of that. Orion, I know with the dome in the foreground, and Sirius. This had a really cool story. They have an all-sky camera. They have all-sky cameras at both Anderson Mesa and the Discovery Telescope, and they run all night and they update every minute. One of the frames on the all-sky camera had a ridiculously bright meteor, and this real bright meteor. And then you could see it on both the Anderson Mesa and the LDT, and you could even triangulate a little bit. You could see that it had a different path just over those 35 miles of difference. And I happen to be doing a time lapse during that. So if you wonder what that green is on the dome, that's a reflection of that bolide, which was to the south. So it's that bright, this bright green thing, which was cool. We had a nice planetary alignment in the morning sky. Jupiter and Venus actually got closer on the next night, and then Mars and Saturn. we had an International Space Station fly over. So these are a bunch of short exposures that make kind of the perspective dotted line that you see there. I told the telescope operator that there's going to be an ISS flyover. And this is at the very end. You can see the morning twilights on its way up. So he had finished the science observations, which always go all the way to morning twilight. They don't waste any time. But he was done with the science observations. And then when I told him that, he decided he was going to try to point the Discovery to a 4-meter telescope and see if he could follow it, and flailed around a bit, but he didn't get it. Oops, just went back up. And a couple from inside. That's the inside of the dome with the winter Milky Way. Orion's kind of racing by. I did a lot of time lapses of this. I'm not going to show those here. Although that's kind of a nice effect when the dome is spinning during a 30-second exposure and the telescope is spinning. So you get the X-ray dome effect where the slit of the dome is sliding by as you're exposing. So it looks like you have open air under the dome. And that's, of course, Orion and Sirius again. Oop, there it again. And finally, nobody but I seem to care about lens balls. I think it's the coolest thing. They sell a thing called a lens ball. It's just a sphere 3 or 4 inches in diameter. And then you can set it on a bottle, and it has to be 4-peaked Scottish ale. So you set it on a bottle, and then you photograph and you focus on the ball itself, which is only a few inches away from the camera. And you point out and you let the depth of field be ruinous, but it makes this really great effect where you see the star colors in the background. So that's actually going back to Anderson Mesa, the 42-inch telescope. And then inside of the lens ball, that's all like in perfect focus, which is pretty cool. And setting one of these shots up is interesting because you flip the center post of the tripod upside down and you photograph up between the tripod legs because it's such a low profile shot. You can't get the tripod to go low enough to take this shot any other way. And finally, lens ball again. And this one is at the LDT, the Lowell Discovery Telescope. And you're kind of getting cropped off in the room here, but that's the summer triangle. So Altair over on the right, Deneb on the left, and right behind stop share would be Vega up there. So it's been a lot of fun going around and taking pictures at the sites. And one other thing is that I'm currently, all that I'm doing is going 3 nights per month, and we're called safety techs. So Jennifer and I go and do split shifts up there, which is you stay in the whole night in a separate room from the only other person that's up there was a telescope operator. And they don't want somebody in the middle of nowhere at Happy Jack up on this hill alone, getting sick or something or tripping and falling. So I take this Red Cross first aid class, like that means I know what I'm doing. And then in case that person has a medical emergency, I call 911 and panic or something. So I shouldn't say that so lightly. And so that's what I'm doing now. But later in the year, last little bit, this is going to be great. October, November, December, I'm going to go back to the 42-inch. They're doing what's called the DART mission, which is dual asteroid. I don't know what the RT is, but what they're doing is flying a satellite into a companion to an asteroid. So this is a double asteroid. One revolves around the other every 11.5 hours. So we're going to fire it into the companion and see how much it changes the orbital period. And the models say it's going to change the orbital period by 53 seconds. It's going to speed it up. And that doesn't sound like much, but after that accumulates, like in a month or two, all your predictions are going to be so far off as it accumulates, and you'll be able to back out how much energy, how much can we deflect an asteroid that's hurtling toward the Earth, like Deep Impact or Armageddon or whatever. So then you can actually find out, here's some actual empirical data that shows how much you're able to deflect an asteroid by crashing a satellite into it. And they need observations, they need photometry. I should have mentioned that when the asteroid's companion goes in front of the larger body, it does an eclipse and an occultation. So a light curve shows a little dip in brightness every time that happens, twice per orbit. And so that's what we'll be measuring with the 42-inch. And I'll be able to do the observations and some of the photometry of it. And that's going to be cool because that actually is NASA funded, and it's going to be 2 weeks in each of those last 3 months of the year. And that's what I'm looking forward to. Anyway, that's my little presentation. Redirection. There we go. I know what's the T there. Okay. Okay. Thanks.
So Tom, before you go, there's a couple questions. Couple questions for Tom Polakis. Grant Compton asked about whether anyone can visit Anderson Mesa or Lowell Discovery Telescope.
You can visit. Microphone. Yeah. Thank you. Question was, can you visit Anderson Mesa? You definitely cannot visit the Lowell Discovery Telescope. There's a gate right away as you go off of Lake Mary Road, and then there's another one right up at the site. So, but at Anderson Mesa, they have visitors all the time. There's like a hairpin turn as you get right to the top. As soon as it flattens out, and amateurs from the Coconino Astronomy Society, Astronomical Society, have observed there quite a bit. And it's a nice dark site. Since I worked at the 31-inch, which is very close to that hairpin turn, if you go there on a Saturday night in the summer, you're going to share it with people who are partying and campfires and that kind of stuff. So it's not the best in that regard, but it is just national forest. It's just Forest Service land, and there are roads that go back in there. You just don't want to drive right to where the telescopes are. There's really nowhere to pull over, but just before that, there's a place where people observe quite a bit, and it'll have that good seeing too.
And the other question was more of a comment about finding your mount for your crystal or your ball. Your ball lens was interesting. The Four Peaks bottle.
Oh, it's called the brand name. It's the brand of that. It's called Lens Ball, like it's one word, LENSBALL. And they're like $40 or something. They come with little mounting hardware, like a little suction cup thing that with the 1/4-20 screw you can put into a tripod. It's definitely going to fall off of that worse than in my Four Peaks bottle, though. That's the best possible.
Yeah, Four Peaks.
It has to be that. Yeah, that's right. So yeah. No drinking at the site. So I've emptied that back at the lodge. So.
Great.
Exactly. Yeah. So Rick asked if the dim, the one star is dim or is fainter than the one image is fainter than the other. That's always the case because one's passing through the wedge and there's light loss through that. And when it's the winter, sometimes there's a lot of light loss through the wedge because it's coated with frost. I learned that the hard way. So yeah, that's not. Oh, Bob. Yeah. We don't, and we probably should.
Can you repeat the question?
Oh, I'm sorry. Being a question. So Bob asked a smart question. That's like, shouldn't you worry about the wavelength? You probably should have even a photometric filter in front of it. And we just use clear. We're getting the maximum light transmission and assuming that the camera is most sensitive near the green, near green. So you're getting a pretty broad band wavelength because the seeing definitely varies. It's worse in blue than it is in red, as you well know. So that would help to have a filter in there. We launched into the thing at Anderson Mesa and did all of those 2 months of data. And then after we were done in the technical review, we were told we used the wrong shutter speed, like we should have used 10 milliseconds instead of 20. And there were other things like that you just say, look, it's a comparison between two sites. And then we got a lot of this resolved by the time we moved to the Discovery Telescope.
Okay, thank you. Okay, give me a moment. I'll close yours.
While Claude's getting that ready, David Dunham mentioned that there's a group that does occultation observations, and you should contact David if you're interested in performing any of those.
No, I think we're good. So here, our speaker tonight is Paul Knauth, and up front here, I did want to mention, if you want to come take a look here up front, Don Wrigley has a eyepiece case that he made. I don't know if it's a cottage industry, if you have questions, or if you want to place orders, but just wanted to show it to you. It's similar to the one that Don and I built for the observatory, and this one has a locking lid, a locking cover, and it's kind of fun. And so for the folks who are seeing and you're looking at this image, here's Paul. He is a professor emeritus at ASU. He's also noted primarily for his field trips, the river cruises or tours to the Grand Canyon for many years, and also the tours at the Death Valley. And he is a true field astronomer. So that's what you see here. He's not only a field geologist, he is a field astronomer. We won't do this after the meeting for the Zoom audience, but here in the meeting room, we will be having an AA meeting. The AA is Aperture Anonymous. I know that many of us suffer from that badly. And like the traditional AA, a support group is really needed. At this point, I'm going to try and see if I can find your file. And I'm hoping that's not it, and that's not it.
We have to wait.
I think James is going to have to do some magic there like before.
This is the Shakespeare room, and I don't know which one it is, Henry III or Henry the something or other play. The theater there was just really barren. I mean, they had almost no sets. So in front of this play, this guy comes out and says, now I'd like for you to imagine that we're on the fields of France, and over here is an army, over here's another army. You know the play I'm talking about? Oh, well.
Oh, there we go.
I can't, maybe
good.
if I quoted it exactly, but I can't do iambic pentameter
We
off
just
the
need,
cuff.
looks
Are we in
good.
business?
Yep. Thank you.
What? We're in business? Okay, so you're amateur astronomers, and maybe we can dim the lights a little bit, or can we? Oh, Zoom. Oh, okay. And we go out and observe with telescopes, and when you get into deepest night sometime, and you've been at it for many hours, you sit down and just stare up at the Milky Way or something. It's actually a great moment. You've all done it. I've done it, and you think deep thoughts sometimes, and almost invariably you wonder, are we alone? Is there someone up there looking at me right now? You've all done that, haven't you? Yeah. Well, it's now science. This Are We Alone? It's called astrobiology. NASA funds it. Our planetary geology program is largely driven. The missions are driven by looking for life as we know it elsewhere. And by that, I mean water-based life, cellular-based life with biochemical reactions that take place in water. And in particular, we'd like to find animals out there somewhere in the cosmos. Well, when this field first started, an amazing book came out by Peter Ward and Don Brownlee, who are extremely credible scientists, to say the least. And they reviewed what we know about life, about biology as we know it, and the conditions it takes to have it. And Brownlee is an astronomer. He reviewed the whole bit about the history of the solar system, about what could have gone wrong in the evolution of life. Peter Ward did the same thing regarding continents and impacts and continental drift and all kinds of catastrophes that could have happened. And they looked at the conditions, surveyed the universe, and concluded that complex life is uncommon in the universe, animals, us, but that bacteria might be quite abundant. Bacteria, that's what astrobiology, according to these guys, is all about. It's germs, and we're looking for germs out in the cosmos. Well, this is just horrible. Well, I'm going to make it more horrible tonight because we don't want germs. We want stuff like this, right? We want aliens to look like this. Some of these are really cool. Some of them are not really cool. But that's what we kind of would like to have. So it says, why is complex life like those creatures is uncommon? And I'm going to alter that. And hopefully by the end of the night, I can very quickly here, I'm trying to speed through this. I'm going to try to convince you, or at least think about why life as we know it is uncommon in the universe. I know we don't want to hear this. We want aliens that look like those. But when this book came out, I thought, my God, these guys missed what I was working on, which I thought was the most important aspect of this. And to understand that, and the argument I'm going to make, I'm going to also note that, like you and me, we've all probably inadvertently swallowed a mouthful of seawater at some point in their life. And you remember how gaggy horrible that is. And when that was all done, you probably wondered, where does the salt in the ocean come from? And when astrobiology kind of started out as a field, there was no real answer for that. You can look in books and news releases, and they say, well, you know, it's weathered out of rocks and has been delivered to the sea over the eons and concentrated there. Well, yeah, that's not true. The Earth, which has continents and an ocean, and yes, we have lots of rocks that are uplifted and shedding material to the sea, chemicals and detritus. But you know what? There's no salt in the Earth's crust, in the silicate minerals that make up rocks. And I don't want to go through this whole diagram. I just want to point out that the Earth is made up mainly of 6 atoms, and 2 of them are silicon and oxygen that are the most abundant, and rocks are fabricated out of these silicon and oxygen atoms, silicate minerals. And there is no room in any of these silicate minerals for a chlorine atom. A chlorine atom is a big old sucker, and it doesn't fit in any of them. There's no atomic site. It's a wrong electric charge for any of these crystal groups. There's a little bit in amphiboles that occur in some rocks, but not much, not enough to supply the salt to the sea. So this was a big problem, and I spent a lot of time thinking about this, and actually got a paper published in Nature and some others. It's kind of speculative, and it's not a quantitative model done on a computer, so it wasn't exactly well received, but it was not disputed. It's just everybody said, oh, what? And I'm going to go through the argument with you for where the salt in the ocean comes from. And once we understand that, oh boy, it'll change your view of things, I think. So salt, table salt, is a combination of sodium and chlorine atoms. And they're arranged in this simple cubic structure. We have a lot of sodium on the Earth. Now, what about the chlorine? So I asked my colleague at ASU, Sumner Starfield, who's an expert on origin of elements, where does chlorine come from in the cosmos? I decided to start at the beginning and think it through using just the standard explanations. I didn't invent any of this sequence I'm going to tell you about. I just incorporated chlorine into it. So it turns out the chlorine atom is produced just before supernova, before a star blows up. Actually, as it's starting to head toward the explosion, chlorine is generated by fusing certain atoms together. And then it's spewed out into the interstellar medium. And here is a big wide field view of the Veil Nebula. Oh, what a great sight in a telescope this time of year, about 2 in the morning. You can see all this stuff. And if you're at a dark sky site, which of course we all strive to go to, right? So this chlorine and other supernova products are strewn out into this medium. And here you can see stars in the Milky Way, star clouds, and you see all that dark dust and gas. That's kind of the interstellar medium. It's denser parts of the galaxy, just the interstellar medium. And it is constantly being enriched by supernovae products. Okay, they blow out, they drift around in the galaxy and get in there. These dark clouds are incredibly abundant in the spiral arms of galaxies, although M31, our favorite here, is got actually very little dust in its arms. Most galaxies, spirals like that have more. Well, here's a view in our own galaxy in the Milky Way, M8, which is another spectacular object visually, and it will be on the meridian in the deep south, probably around 2 o'clock in the morning. And you can, if you have a big telescope, you go to high power, this one's so bright, you can drive around in it and you can actually see these dark clots. And they are these more massive areas of the interstellar medium where material is aggregating together. Now, here's some really dense stuff. And this one down here is a favorite that all of us amateurs like to look at. You're seeing it silhouetted against the Milky Way background, all right? And what is it made of? Well, okay, here's one of them, and this is Barnard 68. There's a catalog of these dark splotches that you can see, and chasing them down in the Milky Way in the summer is a lot of fun. They're no two alike, and they have the most amazing shapes. And you're looking at something that doesn't have any light, but you can see the edges of it as if it did. This one is 400 light years away. Don't ask me how that's been determined. Not that it's too complicated, I just don't know. But then its mass has been estimated to be twice the sun's. So this is something that's where dust and gas is concentrated. It's about 12,500 diameters of a solar system that we're in. This is on the verge of gravitational collapse. It's so dense that it's about to collapse gravitationally. It's just, stuff is just going to tumble inward. These things can get dense and that happens. We can see in an area like this, there are quite a few that are approaching the collapse stage. And the standard theory for the origin of solar systems involves that. It involves a gravitational collapse of gas and dust. Let's fly through the story that a lot of you may already know. All right, this is a pretty hokey PowerPoint cloud, black cloud. And there's a little bit of rotation. It's not uniform, as you can imagine. It's just out there in the galaxy. But once it starts collapsing, it starts gathering in the same direction and spinning, and it spins faster and faster as it contracts. The law of conservation of angular momentum, or what you see when ice skaters pull in and they speed up. So this thing speeds up, and it's been known for a long time that it will flatten out. And so here's a diagram from a book, and that upper part shows the disk of that black cloud has now become a flat thing spinning. This is not my idea. This is the standard story. This is from a textbook. And you notice that in the outer parts of this disk, it's very cold still. And in the center is stars starting to form. This is how stars form. And the residue that's left over forms planets, is the current idea. So here's an artist's view of a star starting to form in the middle of one of these spinning clouds. And as it heats up, it starts to sweep material out. And so there's a new baby star, and the physics of why this thing starts cleaning itself out of gas is a little controversial, but known but there are theories people have converged on. The residue, the solids that have formed, and they're made up of supernova fragments, of dust and elements that were formed in a supernova. They're condensing, they're sticking together. And you know what? A lot of ice. There's a lot of water in the cosmos. Hydrogen is the most abundant element. Oxygen is produced by every star, and it gets blown out not just by supernovae, but at planetary nebulae. It glows a green color that we amateur astronomers love to look at, these green planetary nebulas. And so when all this dust is spinning around this star, it's all kind of going in the same direction. And as it approaches, it sticks together. Now, this is the weakest point in the theory. And I'm not satisfied with any of the explanations, really. We don't understand why this stuff starts sticking together. Man, it really sticks. It almost cold welds. How do we know this? We have samples of it. The meteorites, that's a 1 centimeter cube. And those are little flecks of those particles that were spinning around in the solar disk. And lest you not believe it, I actually have one in my back pocket here. Here we go. I have a sawn slab of a meteorite, which is going to rip my pocket to get it out. I'm not going to ask for help. Here we go. Here it is. Can you see these little white specks? Now, I'm not going to pass this around. You can understand why. This is older than the Earth. It's a rare sample. But you know what? When the meeting is over, you can come up here and form a socially distanced line, and you can hold this in your hand. This is older than 4.5 billion years. And a lot of the little white flecks in here are direct condensates from supernovae, some of which must have been far away. They contain exotic atoms and isotopes that were never homogenized into the material the whole thing disappeared on, formed from. And, you know, this thing, holding this is a real thrill. I mean, I'm always amazed. My hand is almost vibrating, you know, from holding. Well, imagine what this is. This is older than the Earth. This is the very stuff that's stuck. So we know it accretes together. Here it is. And I dare not put it in my front pocket. I'll tell you that. It's a now. So the story then is we start making these things and they grow in size. They start banging into each other. The clumps start aggregating together. And interestingly enough, one of these meteorites in 1999, somebody looked at this. You can't read it, but in the abstract, it says that there are crystals of halite in, that's sodium chloride, in this stuff. The chlorine was made up in the supernova, and the sodium is everywhere. But it got together. There must have been, when it accreted, it must have, the ice must have melted briefly to make, and then as the water evaporated, it made halite, there are actual crystals of halite in this. And you know what? They even have little bubbles of water in them, trapped in them. And that's good stuff. All right, so this stuff starts now gravitationally growing, these objects. And it's a violent event now, it is thought. That's the most popular theory, that this stuff slams into these big ones as it grows and grows. And the amount of heat energy that is released by the impact is enough to literally melt the thing right down to the middle. Better fix my pocket. A bunch of stuff fell out here. All right, so here's a molten mass of one of these early planetesimals. And we really think that the whole thing melted through and through. That was controversial for a long time. It was literally molten rock. And then it started to cool. Things still slammed together. The moon got knocked off the Earth, according to the current theory. But this was a magma ocean, really hot. And also there were a lot of radioactive elements that had been created in supernovae nearby that were incorporated into this, and they were decaying like crazy, giving off heat, and they helped melt the planet as well, the accumulating body. They've all now disappeared. The daughter products are there and we can see them. Some of them are in that little slab if you want to come hold them afterwards. So here's an artist's view of this magma ocean. And here comes the important stuff. Water gets steamed out of there. I don't have to tell you why. Water is a volatile. It doesn't really fit into many of these silicate minerals, particularly the ones that form first from these magmas. So it steams out and we get a water atmosphere is outgassed. There's also CO2, nitrogen, carbon monoxide, what we call volatiles, gases. And one of them that comes out is chlorine. Chlorine is a volatile and it doesn't fit in these minerals, even more picky than water. Chlorine is a volatile that follows the water. It follows the water more than any astrobiologist, they always, their motto is follow the water as they investigate things. Boy, chlorine follows the water. And when it goes into the atmosphere, it becomes HCl, hydrochloric acid. So this early atmosphere of the Earth was a nasty thing. It was over a molten mass, but eventually the molten rock cooled, according to the theory. It's not my idea. Surface cools and the ocean condensed, and we had a primordial ocean that finally formed. And the HCl that was in the atmosphere quickly dissolved, and where'd it go? Here it is. Dissolves in the water, becomes chloride minus, and sucks sodium right out of the rocks. We have a ton of sodium. And bingo, we have a saline ocean. The primordial ocean was a chloride-rich water. How chloride-rich was it? Well, as a matter of fact, this would be the highest salinity, because the water, the theory has all the water coming out right away. It's not something that grows with time. That was a big debate for a long time. And the chlorine came out. And so virtually the entire chlorine inventory that accumulated from the Earth was in the ocean. This was a saline mess. So here's a little diagram. Today's ocean is still salty. It's about 35 parts per thousand salt. But how much was in the early ocean? I struggled with that one for a long time when I was trying to follow this through. And there are ways to estimate it. I won't go into that right now. Suffice it to say that here's a graph showing time going backwards. Today is on the left. We go back 1 billion, 2 billion, 3 billion, 3.5 billion. We don't know much about what was before 3.5 billion because our rock record has been destroyed, probably by a huge rain of asteroidal impacts that came in about 3.8 billion years, if the moon is interpreted. And the issue here is continental platforms formed over time. So that again is something geologists have studied, and the conventional wisdom now is that we had some continental material made of granitic type material. It floats higher than the rest of the ocean basins. And it's, there were little pieces of it around back at 3.5 billion, but around 2.5 billion years ago, there was a big pulse of continent formation. And we see that in the chemistry and a lot of the geology. Not my idea, that's what has come down. And during this time, once we had continents above the water, they get flooded at intervals. Water comes in over the continents, continents bob up and down, sea level rises and falls for interesting reasons that we don't entirely understand. It's not ice that makes the big ones. Anyway, there are times when a place like the Mediterranean basin, if it's under the equator, will accumulate a tremendous amount of salt. Water will evaporate. That's the only way to get salt out of water. If it were easy to get salt out of this primordial ocean, we wouldn't have a drinking water problem right now. Nature does it by evaporating the water. So and when these rare, huge evaporite basins started to form, do you see that we're extracting salt out of the ocean? The salinity is coming down. Now, a lot of times these things form and they wash right back into the sea. We have to find big basins that actually sequester a lot. And they're the oldest that we really know of is around 1.5 billion years. There was a significant pulse. There was a huge pulse 700 million years ago. That's this point right up here on the to the left, that big basin. And then a monstrous pulse that came in about 250 million years ago. So the salinity declines with time, and you can see we had to go almost 1 billion years before there was any chance. The earliest oceans, when these continents were first forming, must have been a real saline mess. Now, how thick was the salt? First of all, we realize it's declining, and getting an estimate for how much was there is a little tough. Here, for example, is a cross-section through North Texas. You see that little geographic map down there in the lower left of that diagram shows Amarillo and New Mexico and Oklahoma. And there's a line called line of section running across it. And that is a cross-section, which if you look sideways at that crossing, this is what the earth looks like under there. And there are huge masses of salt, that white, huge masses of salt. And they were deposited about 250 million years ago. Now, the estimates that you can make for what this original ocean was, in other words, if we put not just all, some people have tried to estimate the amount of salt sequestered on the continents. And it turns out that's not the major source. A lot of that has dissolved and gone down into the deep basin. You drill an oil well anywhere in the world today in a sedimentary basin, and the water gets saltier and saltier, and you get into brines deep down. And if you put that, you can get estimates of how much brine there is lodged on the ground. Put it all together, you can get the least amount would be 1.3 times the modern value. That's if you just did salt. When you start adding brine, it balloons up, and you can, and there have been somebody once made an estimate that there may be, with an amount, what's the amount of salt and brine on the continents? I put that back into the ocean, and it raises salinity about 4 times, which is enormous. You go to the Persian Gulf today, where it's real hot, and there are all these shallow embayments, water's evaporating like crazy. The salinity goes up to 3, 4, or 5. There's some bays there where it's 8. And you know what? There's not a living thing in it except some bacteria. It's what's called, they're faunal deserts. And by the way, those are getting worse because there are all of these desalinization plants where they're taking the water out and then they dump that brine back into the coastal waters. So it's becoming a real issue. Persian Gulf was already had these huge, what they call faunal deserts, no animals living there. Why? Because all life in the sea is stressed. Now, I know it thrives. It thrives, and we have a lot of animals in the sea. They're all fighting this salt. Now, the biochemical reactions get tougher when the salinity rises, and cells have trouble. They have to keep the salt out. And the other problem is as salinity increases, the amount of oxygen that dissolves in the water goes way down. If you have a saltwater aquarium, you better bubble oxygen in it like crazy. And when you get to a certain point, oxygen just won't dissolve in brine. And animals need oxygen to live. And so they start dying off. They have the problem of the biochemistry. They have a problem of no oxygen. Animals don't like saltwater. You get above, you get up to 40, 50 parts per million and you wipe out this communities. Now, it's interesting that the deposition of salt here has not been continuous. In fact, it's just an observed fact that over half the salt in the ground was deposited in less than 100 million years. And it was right up at the very end. In the last 100 million years, there was a supercontinent, Pangaea, and as it started to break up, and a lot of little coastal embayments developed where these green lights are flashing, bars are flashing. Those are sedimentary basins that contain colossal amount of salt. And of course, as the continents broke apart and drifted, they took those salt basins with them. And before this time, well, we don't know what the salinity of the oceans was, but it was higher. Now, the salinity history of an ocean mass on a planet, on this planet, is subject to vagaries of continental drift because that makes the basins, climate, geography, and none of that is programmed into the evolution of the earth. It's all just happens. And if you reran the tape of the earth in its history, you'd probably get a very different set of circumstances, because a slight change in many parameters here can prevent some of this. So very difficult. And I actually published, and I think this is a really cool idea, and it was published in some very good journals, about an alternative possibility for the history of life. This salinity thing bothers the devil out of me. It's been a passion for about the last 15 years before I retired. And the first, like I say, the first billion years, we don't know much about that time, so we hang a curtain over that. But here we are back on our diagram. Now we know we had, or let me put it this way, there's some very compelling evidence that we have things like bacteria in the oldest sedimentary rocks on the earth. Some people are not convinced, but it looks pretty good. So we probably had bacteria that can tolerate high salt. In fact, I once sat in a seminar just before I retired, and some biologist was pointing out that the salt-loving bacteria are the most primitive bacteria based on this genetic sequencing. I don't know if that's held up, but right on, I thought. So the oceans, particularly the early oceans, and by the way, I think the earth was a lot hotter back then there in this time. So you had hot saline water. The early oceans were basically a death trap. So what about the really cool life, not bacteria? So I proposed that actually most of the evolutionary action was in the non-marine, where these little green things are marching up, and that even we evolved animals across all the phyla, living in lakes, rivers, streams, little bitty things like little pissant bed bugs or something, you know, but different phyla were present, because about 540 million years ago, 45 million years ago, there was a tremendous explosion of animal life in the sea. It's one of the biggest mysteries in science. Over a very short time, it may be less than a few million years, 10 million years, 15, all the phyla appeared in the ocean. It wasn't that there was a sequence growing along, just boom, there they were. And boy, did they take off after that. Within 20 million years, the forms of life living in the ocean were amazing. And so what's going on? Well, I argued that this great pulse of salt deposition that occurred about 700 million years ago, it's all over the Middle East. The biggest salt mine in the world is in Pakistan. And it's this ancient salt they're digging around in. That salt, that pulse may have taken the oceans finally down to a salinity low enough that animal life could breathe. And I put that into literature, and people just, you know, they don't say anything. I hardly ever, actually it's starting now. It's starting to be quoted quite a bit. I think, you know, I don't check the metrics anymore about who's quoting my papers. When I retired, I felt like I came out of a coma. I'm having fun now. Why go into this? You know, so life explodes in the seas there, and then land plants get going, and then big animals that have evolved in the sea then climb up out and go back on the land. This is a little bit different. We don't know. This is an idea. The question is, would this happen on all worlds? What is the way in which animal life forms on other planets, other worlds? Well, we think we understand a rough outline of what happened on Earth. And what about some other worlds? Because life did evolve here. And it's amazing. It got going about 3 billion years ago. And while it had crises, it was never totally extinguished. That's amazing. In rare earth, they point out how amazing that is, and that it had a few things been just a little different, the whole planet might have gotten sterilized. So let's go to Mars. That's the one that's really interesting. And what about oceans on Mars? Well, Mars would have outgassed water and an atmosphere. Problem is Mars is smaller, and it loses water. The impacts drove a lot of the early atmosphere off, but it's also just getting blistered by ultraviolet radiation, which breaks the water molecules up. And so there probably was a considerable ocean on Mars. And I'm talking about right after it started cooling down, maybe 4.4 billion years ago or something, maybe even a little bit younger than that. But as the water is lost, I mean, this planet just can't hold the water. It gets concentrated. You start making a chloride brine in these basins. Now, the whole upper probably 100 meters of Mars is rubble from impacts. It's porous, that brine. So the brine would sink down into that, and then actually it would react with the rocks and become a really nasty brine. But I don't want to go into all that. Mars hydrosphere, the salinity, which nobody's talked about, why there should be saline stuff. Well, it's starting to now because they're finding saline waters there. But the basic idea is the salinity increases with time. It just gets worse. Plus, on Mars, being so far from the sun and so forth, that ocean froze. Now, when you freeze salt water, it doesn't all just freeze at once. In fact, what first happens is ice, the water, H2O molecules, form into pure water, ice, and it floats. And as the evaporation goes on, salt condenses, starts precipitating like halite, and there are other salts that sink, other chloride salts, they sink. Now, I'm not going to go through this. The top thing is a official physicochemical explanation, but what we want to look at here is the bottom panel. There's a bucket of brine, and we're going to start freezing this. So we start getting a thick layer of ice at the top. It floats. We start building salts up from the bottom. And now it's getting really concentrated, and the less soluble salts start precipitating, and they rise from the bottom and more ice forms. And then you're finally left with a devil's brew. You're left with all, you know, some of the brines on Earth may have less than 10% water molecules in them. It's just an ionic brew. And you can make those kind of things in this system. Those are called eutectic brines, because on a chemical diagram like that one at the top, that red point is a eutectic point, is the lingo. Point is, it is really nasty. So when the first orbital images, high res, started coming back, Mike Malin's camera, they found these grooves, and they argued that they were gullies and that it was water coming out. They really look like liquid flows. This is about 2001 or something. And so everyone got all excited. There's water on Mars and it's draining out. There is one little problem. It's too cold. That water would freeze at once. So after the news conference where this was released, my colleague Don Bird and I used to go to lunch together all the time and talk science and politics, but mainly science. We decided to figure this out over lunch, and it was really simple. The story, oh, and by the way, some of these are still active. And just recently, there was a report a couple of months ago of a new one that's been discovered, there's a white deposit that's formed there. So Bert and I published this paper in Icarus. It's a planetary geology thing. And we said, eutectic brines on Mars. And we explained in this how you could get these gullies, that they weren't water, they're brines. Not only are they brines, they're eutectic brines. Why? Well, as the water evaporated and then the planet started freezing, you made this salts at the bottom. This would be the water in the regolith, where this rubble zone in the water pores. Salts, you'd have ice at the top, and you'd have this brine here. And since we're at ASU, we call them devil brines. And they would be truly nasty brines. But you know what else? They won't freeze at Martian temperatures. I've analyzed to work on brines from oil fields. You send them to my lab at ASU. And part of the procedure was we would freeze them in flasks with liquid nitrogen. We'd put to freeze them. One day my technician came in and said, this brine that came from this salt mine down in Louisiana won't freeze in liquid nitrogen. I said, what? Now, maybe it was super cool, but that must have been a really devil's brine. I wonder how much of that was actually water. I don't know. She said, if you give me any more of this, I'm quitting. And so now that assemblage that I just showed you, see if it'll go back. That what we call the brine sandwich. Yeah. All right. So in the regolith, that won't last long on Mars. Why? Well, first of all, we get impacts, and an impact doesn't just blast the stuff right at the site. It shovels out all kinds of stuff from the sides. And so you're hurling brine and ice and salt all over the place. It's all busted up. There are volcanoes on Mars, and around them you could get hydrothermal circulation. You could heat that stuff and get the water moving, and you could just have brine separation. It could flow out and go down the walls, the gullies. So that was our idea. And we got all excited and submitted a grant to the NASA Mars Basic Research Program to work this out in detail. And the grant came back rejected, somebody's stamp on it. And it was, the argument was, we've never observed chlorides on Mars. There are no salts. We have analyses of the Martian surface. If you were right about this, if this were worth pursuing, you'd see salts all over the surface. We thought, well, maybe they just haven't been detected. Well, no, we have a thermal emission spectrometer. No, it turns out the thermal emission spectrometer doesn't get a signature from salt, 0. And in fact, that was used in 2008 by people at ASU who run that instrument to point out that a lot of areas where they were getting no signal whatsoever were clearly chloride deposits, were salt. So they published a paper, and boy, there was a lot of hoopla about that in ASU news releases that there are white salts on Mars. And actually, not much of a surprise. There's a Martian meteorite that has been analyzed by Carlton Moore and others, and he showed there was actually salts in a meteorite. I mean, he dissolved some out, a Martian meteorite. So there's Mars, the topography, all that brine that Bert and I think is there down in the subsurface and not good for life. I tell you, no animal will live in that, and I don't think there are many bacteria, any bacteria, could live in a eutectic brine. I made that statement at a conference once, and some lady from Russia stood up and says, well, in our lab, we were finding all kinds of bacteria in brine. So I never saw the paper or anything, but I can't imagine. I mean, that's horrible stuff. You know where it may be going? There are hardly any craters down here in the Hellas Basin, this big blue area. That young surface is forming there. That's the lowest point on Mars. And I think, it's possible that for 3.8 billion years, all that brine has been draining through that regolith. This is very heavy stuff. It can have a density of 1.5, 1.6, 1.4, and it would drain down toward that basin. And I even said at an astrobiology meeting that sent everybody going, rah. I said, I bet if you landed there along the boundaries of the Hellas Basin, you'd sink ankle deep in brine, weeping out from there. Boy, I wish they'd do a mission there instead of these stupid, no, okay, let's not get into that. All right, let's move on to Europa. And Europa has garnered a lot of attention because that is ice that you're looking at. That planet froze. It's way far out. And so there's a cartoon that intrigues everybody that beneath that ice layer, that ice would have floated up and you would have a subsurface ocean. And they put in some hypothetical volcanoes, spewing stuff, hydrothermal vents. We don't know that those are there, but there could be some tidal heating or something. And around hydrothermal vents on Earth, we have quite a bit of life, although it's highly evolved life. So the idea is developed that there should be a mission to Europa. It should be a big orbiter that goes there This lander should come out onto the ice field. In fact, in some area near a little crack in the ice, and we'll take a radioactive bullet, a big thing, and set it on the ice, and it'll melt the ice and sink down through. This is an official proposal. There it is, and see it punching through the ice there in the upper left. A trap door would open, out come a little submarine. It would go around and find all kinds of life there. And there are people who've really been touting this. But you know what? That's going to be eutectic brine. And there's going to be a lot of salt under there, if we're right. But okay, so somebody really convinced the House of Representatives. They told NASA to stop messing around and start planning 2 Europa missions. I don't know where they are, but they're really convinced people there may be life living down under the ice on Europa. And there may be, but it's going to be brine. In fact, the whole reason they think there's water there is by measuring the magnetic field. They see this rocking, and they think there's the changes in Jupiter's magnetic field suggests the moon has a subsurface saltwater ocean. That's right on, and because that conducts electricity. You put a magnetic field swooshing around. And then Ganymede, another satellite of Jupiter, same thing. Look, there's the saltwater ocean, ice floated up, and that brine is going to be eutectic brine. And Jupiter's moon Callisto, there's another one, read the label. An ocean which is thought to be at least 6 miles deep, could be directly beneath the ice. It sure could be. But will it be suitable for life? Here is Enceladus. Now this one's interesting. They observe these things spewing out. They call them cold faithfuls, like Old Faithful. Yeah, clever. And the idea is it's pressurized water that's blasting up. And actually some of the instruments have detected chloride, salt particles blasting out of there. This, by the way, is a theory, and there was a major paper published in Science severely challenging this interpretation. I don't know where all that stands. It's not my field. But my feeling is once that planet froze, and you have eutectic freezing, and that's why you have ice on the surface. And then you go out to Saturn. Now Saturn's moon, Dione, a subsurface ocean lies deep within Saturn's moon Dione, according to new data from the Cassini missions to see. I was walking along with a person who was interviewing for a job at ASU, and I asked her, I said, you study these salt or these ice worlds. Do we really know that there are oceans under these? Her response was, absolutely. And then I figured they don't know. It's a theory. Okay, so Saturn's moon Titan. Oh yeah, so Titan is believed to have a salty subsurface ocean, as salty as the Dead Sea on Earth. And down underneath all that. Could be. These are not dumb people that are proposing. They got data that's, but how much salt? It's going to be eutectic brine. Asteroid series, yep, even an asteroid. You got a thin, dusty outer crust, rocky inner core, and the rest is water ice. And that's based on the density. I wonder, by the way, if they used the density for brine, which is much higher in that calculation. Anyway, I don't know. Well, we're going on out to Pluto. Well, yeah, maybe it's hiding a giant habitable ocean. This one guy they're quoting expressed no doubt Pluto indeed has an ocean. It could have an ocean, but what's the nature of it? There's a paper. I won't go. This is far from the sun. It is really cold out there. I don't know. And Chiron, even the moon of Pluto is supposed to have an ocean underneath. So you get on out to the outer solar system into the Kuiper Belt, and we actually have identified a number of objects there. They appear to be icy objects, have icy surfaces. So again, people are speculating they have oceans and ocean worlds, subsurface oceans. It's a big rage right now in the scientific community. Not subsurface brines, subsurface oceans. You know, I was at a conference once, an astrobiology conference, and somebody I was talking to one of the guys who was on one of these lander missions, and he said, we have some kind of stuff forming and it looks like it's liquid. And he says, but it's too cold. And I said, well, it could be brine. And he says, we do not use the B word. In other words, bad for astrobiology. So, but that was, I don't know, he was smiling when he said that. And even comets, people are saying comets may have life in, or had life in their cores. So what we're looking for is a pale blue dot now in terms of exoplanets. And, you know, they might just, these people are very clever. They just might start imaging. This is the Earth, of course, from one of the Voyager missions way out as it left the solar system. We're kind of looking for that. And I tell you, they're probably going to find one. There's so many exoplanets and the technology is just amazing, especially these satellite telescopes. So the pale blue dot. Now, when they find it, there's going to be a celebration like you can't believe. They found an ocean world, and where there's ocean water, probably life. Well, it's probably brine, first of all, maybe bacteria. If they find a lot of ice on it, it's going to be a eutectic brine. And yeah. What now? Suppose they find a pale blue dot with brown spots on it, and maybe even a green spot. Now we're talking, because there you could have had continents where you could sequester water. Right. And is there any place in our galaxy where we don't have, where we have less chlorine? You know, really not. There's supernovae all over the galaxy. In fact, they're worse down toward the core. So the take-home message of that little exercise is chlorine is produced throughout the galaxy. It follows the water. Early hydrospheres are very saline and likely to get saltier with time unless continents are there. How else are you going to get rid of the salt? And subsurface oceans, on the island, if they get, are necessarily very concentrated brines. Maybe even if they froze, if it was originally water that froze. It's a salty universe, and this is depressing. Now, just a couple of closing points. Stephen Jay Gould wrote this amazing book called It's a Wonderful, Wonderful Life. I guess the movie is It's a Wonderful. Anyway, talked about the Burgess, and his major point throughout this wonderful book was that if you ran the tape of evolution of life on the earth, animals, you would not get the same animals. That there's so much chance, so much contingency in the events that happen. And he develops that throughout this book. Now, some people have objected to that. There's even a book written to try to counter this, but he makes a very compelling case. And then there's Ross Taylor's book, Destiny or Chance, required reading. It's probably on Amazon. And he talked about the origin of the development of the solar system over time. And his argument was that you rerun the tape of origin of a solar system and you won't get the same solar system. There's so many chance events, so many variables in the thing. And I once got on a plane in Dallas going to Denver for some meeting, and Ross Taylor was sitting in the middle right next to me. I'd never met him. I had an amazing conversation. This guy is brilliant. And this was a beautifully written book. And by the way, he did a revision because when he wrote it, there wasn't much data from exoplanets. And by the time he wrote this book, there was a lot. And you know what? There are no two solar systems the same. The exoplanets are coming out all different. And so this idea that, there's a orderly way in which animal life develops on the earth can be contested from a lot of different angles. My angle is the chlorine. That's the only one I know a whole lot about. So what have we got here? We got this nervous system. That's what that is, with this huge brain. And life as we know it, animal life, evolved this conscious nervous system. in a thin water film on a tiny solid planet. The reason I say a thin water film, if you had the Earth, if you reduce the Earth to the size of a basketball, the oceans would be like a sheet of thin paper on it. It's a film. And here is where the universe became conscious of itself. It took 4.5 billion years. And really, it's only in the last 500,000 years that brain got big enough to become conscious the way we like to think of it. And its evolution, this nervous, depended on many chance events. So the question arises when I'm out with a telescope and I take a break and I stare up at this cosmos. I see my big telescope silhouetted against the stars, and computer-driven motors are holding the thing fixed in space while the Earth rotates under. And if you think about that, you kind of get carried out there. And I quit thinking about animal life anywhere. It could be, but it's so unlikely. Even bacteria. I think they overestimated in that book, Rare Earth, because they didn't consider brine at all. Words not in there. They didn't know. I wrote a paper now. If they didn't know now, I would roll it up and beat them over the head at the next meeting I saw them. Now, the question I think when I sit out there is this the only way consciousness develops in the universe? That is the question. That is the question. I mean, what we've got here is a nervous system in a pile of meat. Really? This is how it works? So the question is then, well, how else could it happen? And do you know what the answer is? If you do, tell me, because I don't have a clue. I don't even know how you address the problem. I don't even know the questions to ask about consciousness out there. It's we can't get our arms around it. You can't use any known science to get at it. But God, what an interesting question it is. So the other thing I do during breaks now, instead of torturing my mind with these questions, is crazy stuff like shooting a laser at the core of the galaxy, seeing if anybody answers. No, they never have. But more importantly, you know what? It's wasting time sitting there. If you're out there on a beautiful night, get with that telescope and just look at, forget light. Look at all the amazing things we have, the galaxies, no two of them the same. You can see them in these telescopes. Spiral arms, some of them are interacting. You can viscerally feel parts of the galaxy being tugged. You can see them warped and peeling off. We look at glowing clouds of gas in our Milky Way. They're beautiful and mysterious. You can drive around in them. Some of them are so big. If you have motorized controls, the bigger the telescope, the better. It's star clusters. They're like little baskets of gems, you know, and then there are the globular clusters. What in the world? How did they form? All these things are being addressed by science, and they are truly rewarding to read about. Planetary nebula, which blow off these clouds, filaments, halos, hazes, and there's so many you can look at. They can take all the power you can get. No two the same. No two the same. And then we've got comets. We've got supernova remnants like the Veil Nebula and a lot of others. And boy, some of those are spectacular. We even have supernova you can look at. If you follow the news, astronomy news, sometimes some of the galaxies have a little star that appears in the tip. That's a supernova. You can actually see one. I always think chlorine, you know, and I see it. And by the way, with my 25-inch, I have discovered numerous supernovae in galaxies until I got down off the ladder and looked at my atlas of galaxies on the observing stand, and I find it's just a field star. It's been there since 1990. That's not, it's just in the way. All of these great things to look at. And then there are planets. There's the zodiacal light. You don't even need a telescope for that. Whoops. Oh, so what I do, I just climb my ladder and exult. You know, just This is fantastic. You know the feeling, and if you want to do that at a star party, just do it. Nobody cares. We're all amateur astronomers, and we're out there to feel the universe coming. But as for bacteria and animal life and all of astrobiology, well, I don't know. So I believe thanks for your coming tonight.
Question. You mean we hang on the microphone for a minute?
Will you watch this meteorite?
James, do you have any questions?
Sure, we got one here coming in. Is Death Valley a salt basin?
Is Death Valley a fault basin? What? Salt basin. It is indeed. And yet salt is derived from rocks. It does weather out of rocks, but it weathers out of rocks that have salt beds in them. Okay. It's not. So the answer is yes. It's also got gypsum.
That's the only answer or question I got.
Okay. Okay, well, if you want to see this meteorite, come on up. I don't know, Zoom people are just out of luck, but you all who came tonight, feel free. It's been a long sit.
So let me see if we can think. So as we go through tonight, before you all disappear, we would like some help putting up the chairs. It's nice to see so many familiar faces, but it's also nice to see a lot of new faces, folks I have not seen before. So come by and say hi and let me know. But we will see you next month for our next hybrid meeting. So thank you very much. Paul, thank you again. We really appreciate it. It was a wonderful presentation.
Some people might go there.
Some folks are going to go to the Union Tap on Higley, north of Baseline.